This is the video for section 4.1.3, non-homogeneous equations. So in this section, we are going to be interested in nth order linear differential equations that have on their quote-unquote right-hand side a non-zero function. And so we're going to be interested in writing down the general solution to such an equation. So let's consider a differential equation of this form. Now in this video and from here on out, L is going to be an nth order linear differential operator. And it's going to satisfy the conditions of the existence and uniqueness theorem, namely all of its coefficient functions are continuous on some interval and the leading order coefficient function is non-zero on that interval. Okay, so we have our non-homogeneous linear differential equation, which I'll denote NH. And let's suppose that y sub p is a particular solution of this differential equation. No comments yet about how we'd find such a thing, but just suppose you woke up and you thought of a particular solution to this non-homogeneous equation, so you just happen to have it. Then we write, our notation is that L of yp equals g of x. That's what it means to be a solution of NH, of our non-homogeneous differential equation. Now suppose also that you have a fundamental set of solutions to the corresponding homogeneous differential equation. Now we remember that if I have a homogeneous differential equation where I have an nth order linear differential operator, I'm guaranteed the existence of a family of a fundamental, a set of fundamental solutions to that differential equation. So my claim is that the function given by c1y1 plus ... cnyn plus my particular solution y sub p also solves my non-homogeneous equation for any choices of the CIs in the reals. So I claim that if I have a fundamental set of solutions to the homogeneous differential equation and one particular solution to the non-homogeneous equation, I claim a function of the form written here is also a solution to the non-homogeneous differential equation. So let's see how that proof goes. So I will write L of y, which if I expand y to how I defined it, I have L of c1 y1 plus ... cn yn plus yp. And then I can use the linearity, I can use the linearity of L to get that this is equal to c1 L of y1 plus ... cn L of yn plus L of yp, and then as you just saw, the punchline is that all of the fundamental solutions, L applied to all of the fundamental solutions equals 0, because that's what it means to be a solution to the homogeneous differential equation. So all I am left with is L of yp, and we know since yp solves the non-homogeneous differential equation, this equals g of x. So in fact, y written as a linear combination of the fundamental sets of solutions plus my particular solution, that is also a solution to the non-homogeneous differential equation. So we are going to be interested in finding a general solution to the non-homogeneous differential equation. And our theorem is going to be that I can do that if I am given a particular solution and a fundamental set of solutions of the homogeneous differential equation. So the claim is that the general solution of the non-homogeneous differential equation is given by this, what should look familiar now, y equals c1 y1 plus ... plus cn yn plus yp, where again the CIs can be any real numbers. So we just proved that if I had a function of this form, that it solves the non-homogeneous differential equation. So the only thing we need to prove to say that in general this is the general solution, the form of the general solution, the only thing I need to show is that if I have a solution to the non-homogeneous equation, it can be written in this form. So that's what I'm going to show now. So let's suppose that I have capital Y is just some solution to the non-homogeneous differential equation, and Y sub p is my particular solution. So what I'm going to want to show is that Y, capital Y, can be written in the form as written in the theorem. So I'm going to define an auxiliary function, u, and I'm going to define it to be big Y minus Y sub p. And you might think about why I would like to do that, and we'll see here in a second why I did that. So what is L of u? Well, L of u equals L of y minus yp, and now, like I said in class, linear operators are basically the best thing ever. This is equal to L of y minus L of yp, and since both of those solve the non-homogeneous equation, that's g of x minus g of x, which equals 0. So L of u equals 0, which means that u solves the homogeneous differential equation. And now, since you're experts on the homogeneous differential equations, you know that that means we can write u as some linear combination of my fundamental set of solutions. So, namely, there exists constants c1 through cn such that u equals c1y1 plus ... plus cn yn. Now, if we go back to how we defined u, if u was y minus yp, that means capital Y equals u plus yp. We just showed that u had this form of a linear combination of my y sub i's, so that means big Y is c1y1 plus ... cnyn plus yp, and that was exactly what we were trying to show. We were trying to show that any old solution to the non-homogeneous differential equation had this form. And we have names for these. That first bit, that linear combination, we call that the complementary function, and then the y sub p is my particular solution. So let's just look at a little example of how this works. Again, we have not said anything about how we're going to actually find these solutions. We will get there, I promise, very soon. But if we have a set of fundamental solutions as well as a particular solution, that allows us to write down the general solution to a non-homogeneous differential equation. So here's a perfectly good non-homogeneous second order linear differential equation, y double prime plus y equals secant of x. And I would like you to verify that cosine x and sine x forms a fundamental set of solutions to y double prime plus y equals 0. So you need to check they are both solutions, and you need to check that they are linearly independent. What I would also like you to check, and this is just some good differentiation practice, is that y sub p equaling x times sine x plus cosine x times natural log of cosine x is a particular solution to our non-homogeneous differential equation. And when you do that verification, you're going to need the Pythagorean identity sine squared x plus cosine squared x equals 1. So if we do that, then the general solution to y double prime plus y equals secant x is, by our theorem, y equals c1 cosine x plus c2 sine x plus our particular solution x sine x plus cosine x natural log of cosine x. And again, that first piece, those first two terms are my complementary solution, and those last two terms are my particular solution.